Alright everyone, here are the 3 examples. I know this is a long video, so you don't have to watch each one. These are the examples. Find f prime for f of x equals the square root of x. So if you have a problem with that one, you can watch this one. Otherwise, skip a little bit ahead and you'll find the function for f of x equals absolute value of x minus 2 is continuous at x equals 2. Find f prime at x equals 0. It should be at x equals 2, not x equals 0. It should be x equals 2. And that's okay. I did x equals 2 in the video anyway, so that's alright. So if you don't know absolute value or something like that, so that would be the next one. Or the last one is f of x equals 1/3 x. Find f prime of x at x equals 0. So if you want to figure out how to do any of these, you can skip around. You don't have to watch this whole video. Alright, and enjoy! Alright everyone, welcome to 2.1 part 3. Here's a couple more examples in case you get to the assignment and you don't exactly know what to do. So here's another example. Find f prime of x for f of x equals 1 over the square root of x. Then find the slope for the graph. I'm sorry, it's not 1 over. I'm sorry, it's f of x equals the square root of x. That p looks like a 1. It's not. Okay, so find f of x equals square root of x, then find the slope for the graph at the points 1, 1, and 4, 2. Discuss behavior of f at 0, 0. Alright, so what we're going to do is we're going to plug this in. We're going to say the limit as delta x approaches 0. And this time I'm just going to plug it right into the square root of x plus delta x minus the square root of x all over delta x. Right? So I skipped it writing the function part first. Not really a big deal either way. If you're comfortable writing it this way, you can. If you want to write it the other way first, you can do that as well. Alright, so now what we're going to do is we're going to do a little trick that's going to be called rationalizing numerators. Rationalizing the numerator. Alright, just like remember when we were rationalizing the denominator, you multiplied by the square root or the complex conjugate or things like that when we were trying to get the denominators to be whole numbers or getting rid of those ugly things that we didn't like. Well, now we're going to do the same thing with the numerator. So what I'm going to do is multiply the top and bottom by this plus this. That way we don't get any stuff in the middle. So we should look like this as I get limit as delta x approaches 0 of the square root of x plus delta x minus the square root of x, put that in parentheses, times the square root of x plus delta x plus the square root of x, and that's going to be all over delta x times the square root of x plus delta x plus the square root of x. Alright, so all I did was multiply by the conjugate of our top number. Okay, so now if I FOIL, I will get the limit as delta x approaches 0. If I do this one times this one, I'm just left with x plus delta x, right? And then I'll do this one times this one. What I'll have is the square root of x times the square root of x plus delta x. And how many of those will I have? None, because I have a positive one and a negative one. So we have square root of x, x plus delta x. So these two should cancel out, which is kind of the idea. And we have minus x square root of x plus square root of x. It's just going to be minus x all over. What I'm going to say is just I'm going to leave this as delta x, and then I'm going to have the rest of it. So that is the square root of x plus delta x plus square root of x. Okay, seems confusing at first, but it's just FOIL with some extra stuff. So we didn't even need to write this. That is extra. So we know that was going to cancel out. We knew it because that's how we chose it, because it's minus and plus. Alright, so we can now simplify as much as we can, and we're going to get this x and this minus x cancel out just like they should every time we do these because it's in part of the formula. Okay, and so we're left with delta x on top over delta x, and then we have the square root of x plus delta x plus square root of x. Okay, these guys cancel out and we're left with the limit as delta x approaches 0. And let's make sure it approaches 0 the last time. I said it. I also just wrote it. You can't go back to the video and look at it to see if I did it wrong or something, right? No, of course not. Okay, so it's going to be 1, right? That's in the numerator, over, and we're going to say the square root of x plus delta x plus the square root of x. Now that we've simplified it as far as we can, now if I plug in 0 in for delta x, am I going to have a problem? Well, it's going to be the square root of something plus 0. That's still going to be that same thing. I'm not going to have a problem as far as getting an answer. So I'm just going to write this on the same line because it's going to be a little bit easier to write. So the limit as delta x approaches 0 is going to be 1 over, and I really have the square root of x. I'm just going to do a little bubble here. The square root of x plus 0 plus the square root of x. Right? Square root of x plus 0, same as square root of x, and I have another square root of x, so really I have 2 square roots of x. Okay, so it's going to be 1 over 2 square roots of x. And that is going to be f prime. So we can write this as f prime, the derivative, aka the slope, let's say f prime of x equals 1 over 2 square root of x. So there's our f prime, which is what we're trying to find. Okay, so it says find that, we did all that, then find the slope for the graph of the points 1, 1, and 4, 2. So I need 1, 1, and 4, 2. Okay, so all we have to do is plug in 1 in for x and see what happens. So I have f prime of 1 is going to equal 1 over 2 times the square root of 1, which is just 1 over 2. So the slope should be 1/2. And then what I'm going to do is f prime of 4 is going to equal 1 over 2 square root of 4. Square root of 4 is 2 times 2 should equal 1 over 4. So there's my slope at 1, 1, and there's my slope at 4, 2. Okay, last thing it asks us to do, discuss behavior at 0, 0. So if I plug in 0 in for that x, I get 1 over 2 square root of 0. That's going to be 1 over 0. And that's going to be, uh-oh, we have a problem. So if we have a problem like that, if you think about this in a way that makes sense, go back to thinking about slope, what happens when the slope does not exist? What type of line is it? And you say, well, it can't be a horizontal line because that's when y equals 0. We had a problem, we couldn't write the equation when it was a vertical line, like that, right? So this will tell you that the slope is vertical. We have a vertical asymptote at 0, 0. Okay, so now if we actually go back and just look at the graph real quick, we didn't look at the graph at all, and we could have, but let's do that now. Here's the graph of this function, right? So we say at 1, 1, there's our slope of 1/2. At 4, 2, our slope is 1/4, exactly what we got. And then at this point right here, we're looking at 0, 0. It's actually right here. See, the slope is completely vertical, so therefore you're going to get divide by 0 because it doesn't have a slope. The slope is vertical. So there we go. We did everything correctly. Let's keep going on to the next 2 examples. They won't take as long. That one was pretty involved with that rationalizing the numerator. Okay, the function f of x equals x minus 2 is continuous at x equals 2. Find f prime at x, f prime of x at x equals 0. Okay, so we're looking at this absolute value function. That minus 2, which way did it shift? Because it's minus 2 inside those parentheses, or absolute value signs, that means minus 2 moved it this way, right? So it should be 0, 0, moved it to 2, 0. Okay, so we know it's continuous here, but what happens when it's kind of at a sharp turn, a point here? What's that slope going to be? Because it goes this way, and then it goes this way. It kind of turns really sharp. So how do we define that slope? Okay, so what we're going to do is we're going to look at it from both directions, right? We're going to look at the limit from this side and from this side, and we're going to say what happens in between. Okay, so what we're going to do is we're going to say let's find the limit as x approaches 2 from the right side of our derivative function, right? So that means it's going to be the absolute value of x plus delta x minus 2. Oh, maybe not. Let's just do x. Let's just do x minus f of 2. So we're going to say f of x minus f of 2. So that means we can say that this is the limit as x approaches 2 from the left side of the absolute value of x minus 2 minus the absolute value of 2 minus 2. And I'll leave this all over x. Okay, and then actually what we're going to do is I'm going to try and do the parallel thing on the right side. We're going to say what's the limit as x approaches 2 from the right side, and that's going to be the same thing as going to be the absolute value of x minus 2 minus 2 minus 2 all over x. Okay, So what I can do is I'm going to plug these both in, and I get 2 minus 2 is 0, 2 minus 2 is 0. So x minus 2 divided by x as it approaches from the left side. If we think about that whole thing, the limit as x approaches 2 from the left side. Let's take a look at that one real quick. Alright, made a small mistake. We're going to fix it. It should be x minus 2 in the denominator. We're going to say, because we want this whole thing to get as close to 2 as possible. That's why it should be x minus 2, not just x. So, first mistake I've ever made, you can document it here right on this video. Alright, so what we're going to do now, we know this cancels out, and we're going to say the absolute value of x minus 2 all over x minus 2. And we're going to do the same thing as the limit as x approaches 2 from the positive side of x minus 2 over x minus 2, absolute value on top. Okay, so let's just give an example. Let's say 1 from the left side. 1 minus 2, negative 1, absolute value equals 1, over 1 minus 2 is negative 1. So this thing is going to be negative 1, and you can try other values, and it's going to be negative 1 every time. If we go to this side, let's pick a number like 3. So 3 minus 2 is going to be 1. 3 minus 2 is also 1. So I have negative 1 here, and I have positive 1 here. We've got a problem because the slopes are not the same as we approach that negative 2. So that means we can say that this thing, I'm going to even write this in a different marker, because it's a slightly different way of saying it. It's just wording notation. We'd say f of x is not differentiable at x equals 2. Okay, it can be differentiable at other places. We can find the slope at when x is 1, x is 2, well not 2, x is 1, x is 3, x is 5, 7, 8, 9, 10, 11, 12, 12 and a half, 13.74, 2, 1, 8, anything but 2. When it's at 2, at that sharp turn, at that V, right at the bottom, there's the problem. Alright, because it goes from this way to this way, and we don't know what the slope is at that point, right? Because it's changing from negative to positive really, really quickly. In that one instant, it's changing from negative to positive. So we can say it's not differentiable. If they don't go towards the same thing, if the limits don't go towards the same thing, negative 1, positive 1, it is not differentiable. Okay, now here's example 3. F of x equals f of x equals x to the 1/3. Find f prime of x at x equals 0. Okay, so then we're going to go through and we are going to do this again. I know this video is getting a little long, but you can always skip around. You might say, oh, I want to look at this one, I want to look at that one. I might do a quick thing for you just to remind you of that part. Okay, so we're going to say the limit as delta x approaches 0. We're going to say delta x approaches 0. Hold on a second. Maybe I can make this a faster way. I can make this a faster way. So here's what we're going to do. It's going to be as x approaches 0 because we're trying to find at 0. So we don't want to start at 0 and get really, really close. We're going to say x is 0 and we can find some small changes. So okay, so we're going to say the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. Okay, there we go. So f of x at that whole thing, we're going to say the limit as x approaches 0 of f of x is going to be x to the 1/3 minus 0 to the 1/3 is still going to be 0 all over x. Yes? Right. Good. So we have limit as x approaches 0 of x to the 1/3 over x. I have the same bases, so what are you going to do with the exponents? You subtract them. 1/3 minus 1 is negative 2/3. Or we can say this is the limit as x approaches 0 of 1 over x to the 2/3 power. Okay, so now what we're going to do is we can say, let's think about this. As x gets really close to 0, this whole thing is going to get really close to 0, right? If you take 0.1 to the 2/3, it's going to be a very small number. All right, 0.01 to the 2/3, it's going to be a very, very small number. We're going to keep on going. It's going to get very, 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 very small, which means 1 over a small number is going to equal a very, I should say, a big number. Right? And we could also say 1 over a very small number is going to equal a very big number. Alright, so if we get closer and closer to 0, as we approach 0, this whole thing becomes really close to 0. This other thing, 1 over a very small, becomes a very big. So we can say this limit is going to equal infinity. Alright, which means we probably are going to have, if it's infinite, that means we're probably going to have a vertical asymptote, or a vertical slope. Alright, so let's see if we look at this graph. There it is. There is our f of x equals x to the 1/3 function. We can say f is not differentiable at x equals 0 because f has a vertical tangent at x equals 0. It's vertical. We can say that slope is infinite, which means it goes completely up. So we have, if we're following the slope, there it goes this way, and we go along the graph, it starts to go quickly, and then there it is, completely vertical. And then as we go to the right more, it starts to level off, and it levels off fairly quickly. See? I guess I could do a better job of trying to look at it, but you get the idea. So at this x equals 0, we're going to say it's not differentiable because it is infinity at that point. So again, for this one, you're going to say it is not differentiable. Alright, see? There you go. And that is it. I know it's been a long time, but good luck with the rest of your assignment.